I'm Hong from Penn State, and this is a work collaborated with researchers from Chinese Academy of Sciences and also Qianxin Company. So this work is about how to test the binding code of scripting language with a new method called cooperative mutation. So these days, the script language, like JavaScript or Python, are so popular, easy to learn, easy to use. Actually, it has been integrated into other popular documents. For example, you can use JavaScript in HTML or even PDF. And also for the VBA from Microsoft, you can use this one to manipulate the Word document or PowerPoint. So that's great. That'll simplify our Word. Actually, the program is more complicated. The complexity leads to a lot of bugs. Actually, we have seen so many dangerous vulnerabilities in these programs we use daily. So to detect these bugs, we proposed a solution called Cooper that are going to use cooperative mutation to effectively test the binding code of a script language. So in total, we found 134 bugs in these commercial closed source programs like Adobe Acrobat, Foxy Reader, and Microsoft Word. And this resulted in 33 CVEs and 22,000 bug bounties. So our tool is available online. You can try and see whether you can find more bugs or get more bounties. So before I go to the details of the tool, let's check some internals of the document and also the applications. So these days, because of the integration of the script language, the input actually contains two parts. First part is a native object. Like for PDF, this is a text, images, annotations, or others. Another part is the script language, which is JavaScript here. So correspondingly, for the application, they also have two components to process these two parts of input. So they have some native modules to understand the PDF and to display it to users. And also, they also have a language interpreter to understand the script code and to execute them. So because these two parts are kind of independent, so they must, the developer independently, they must have a binding layer to talk to each other. They're going to translate this data and also transform the representations. So the binding layer is very complicated, and it's very hard to be always correct. They have a lot of bugs. So previous work, like the Pivocado in the last year in DSS, they have been trying to synthesize the script code to trigger bugs. However, we realize this has some limitation. Some bugs cannot be triggered this way. So here is one example. So this is a heap buffer overflow in Adobe Acrobat. So attackers can use this bug to run arbitrary code on the victim machines. Because of reporting this bug, we were awarded a 2,500 bounty. So how to get the bounty? How to trigger this bug? So there are two steps. So first, you need to insert one extra element into this array. So by default, they have only 256. Now they have one more. Another step is you need to invoke this particular JavaScript code with change the zoom tab of this page into the refw. So if you do both, you can trigger this bug and get the bounty. But apparently, if you use one-dimension mutation, which means if you only modify object or only modify the script, you cannot trigger this bug. So inspired by this, we propose a solution called cooperative mutation, which modify both the native objects and also the script language. So the question here is how to mutate them, so-called cooperatively. So our insight is we should find the relationship between two parts. And if we know the relationship, we should mutate them in a corresponding way, and we can trigger deep logic of the program and find more bugs. So the challenge are follows. So first, how to find the concrete relationship between two parts? It's going to be very complicated. I mean, if you check the menu of Adobe Acrobat and JavaScript, it's going to be hundreds of pages of menus. We want to find a scalable way and automatic way to find the relationship. And second, if you know the relationship, how do you guide the mutation to find more bugs? So these are the two challenges we have. So when we're trying to solve these two challenges, we realize it's another big problem, as there are too many objects and code here, and the relationship is very complicated. You don't want to spend too much time to identify the relationship for each pair of them. So we're trying to group them into different classes and groups to simplify the relationship. So fortunately, the previous work of Pivocado have handled the code side, so we just need to worry about how to class the native objects. So we design our tool Cooper in this way. It takes some sample documents as the input and also finally generate the bug report of the application. So it has mainly three components. So first, it tries to cluster these native objects into different groups and classes. And second, we're trying to automatically infer the relationship between code and object. And finally, we use this infer relationship to guide our mutation. So let's quickly look into them one by one. So the first step is to cluster objects. So we observe that in most of the document, the object is actually described by attributes. For example, the font, the size, color. So the attribute have a name and also have the value. The value could be another object. So because the name have some semantics meaning, we decide to use a name to cluster objects. So the idea is like this. If two objects ever been used as a value of the same attribute name, we're going to group them together as one class. For them here, we have a font class, and also we have the annotation class. So this is the brief idea to group objects. Of course, this is have some accuracy. We plan to use we use the attribute similarity to further split or merge different classes to get a more accurate result. So basically, we use the dice distance to calculate the similarity between different classes and decided to either split it to more smaller classes or merge into larger ones. So this way we can get a more accurate class result. You can find more details of this part in our paper. So the second step is how to infer the relationship. We want an automatic way, scalable way to find this relationship automatically. So here's what we do. So we collect a bunch of documents, for example, PDF files. And also we prepare a bunch of very simple code snippet to use this API, this code API. And we insert every code snippet into every document and try to use the application to open this automatically. So if this execution succeeds, and we're going to record this. And of course, if it fails, we also record this into failure site. So by trying this again and again, we get a huge record of failure cases and success cases. And with this, we're trying to infer the relationship automatically. So we're going to draw this table. So in this table, each row is actually a class of the object, and each column is one group of code we call API. So the success rate means among all the documents that support this API, make it execute successfully, how many of them contains object that belong to each class. And also, we also calculated the failure rate, which means among all the documents that make the API fail, how many of them contains objects in each class. And finally, we use the difference between the success rate and failure rate to estimate the possible relationship between the object and code. So here we never confirm this relationship. We never know what is the relationship, but we just estimate it this way. So we find all the difference, and this is the estimated relationship. Next, we're going to guide our mutation. So our mutation starts from the APIs, which is the code side. We're going to select a bunch of scripted APIs and use the existing tools to generate the scripted code. This is not our contribution. So we're going to use the table, the relationship table, to decide which objects are most important, are most related, and use this one to decide which object to change to trigger more bugs. So finally, we propose several ways to do mutation. I'm going to leave these details to the paper. So finally, we modify both script and object in parallel and in this under the guidance of the relationship, and finally generate new documents for testing the program. We implemented our tool Cooper with 4.3 lines of Python code. So currently it supports two formats, PDF and Word document. And we just use existing tools to generate a script, for example, Tomato. This can be replaced by any script generator, like even Avocado or Freedom. And our solution is extensible. Currently, we are supporting the HTML plus JavaScript, and we plan to release that also in the future. So we evaluated our tool in 2 dimensions regarding bug finding and branch coverage. So within 4 months, we found 134 bugs in these 3 closed source huge programs, including Adobe Acrobat, Foxy Reader, and Microsoft Word. And this resulted in 33 CVE numbers, and 59 of them has been fixed. And we got 22,000 bug bounty. And these bugs are triggered by 90 different API groups and also 11 object classes. We also evaluated our tool with different configurations and compare with others. So here, the Cooper 4 is the full-featured Cooper with all the features. And Cooper Random is we just randomly modify both objects and script, but without any guidance. So Cooper Object only modify object, but with the guidance a little bit. And the Cooper Script only modify the script side. And Tomato is the existing tool that can generate the JavaScript code. We modify a little bit to make it support the PDF. So this is the result. This is the evaluation result of bug finding within 1 week. And you can see the full-featured Cooper find the most number of bugs, which is 18. They are unique bugs, which is manually confirmed. And without the relationship guidance, it finds 12 bugs. And if you only modify script, you can still find 8 bugs, but much less than the full featured Cooper. And Domato find 6 bugs. And if you only modify the object, you can only find 4 bugs within 1 week. So which means that the full featured Cooper, with all the guidance and also modify both object and script, can find the most number of bugs within 1 week. We get a similar result for Foxit Reader, but I'm going to skip the details. Anyway, the full featured one achieved the best result. We also measured the branch coverage. Notice that the Cooper does not rely on the code coverage as a feedback to guide mutation, but we just measure this to understand why we can find more bugs. So here is the evaluation on Adobe Acrobat, and this is on the script parser side of the Adobe Acrobat. So the full featured Cooper achieved the best code coverage, and if you only modify the object as expected, it achieves the least coverage for the script interpreter. And others just achieve the coverage in the middle. Surprisingly, we also measured the other part of the Adobe Acrobat, which is the native object processors. All two also achieve the best result. The difference here is that if you only modify the object, it's not the worst anymore, because this is the native coverage. We also measured the other tools like Foxit Reader and Word, and we get a similar result. So all two always achieve the best code coverage. I guess this is the reason we can find more bugs, but we never confirmed this. So in summary, we proposed Cooper, which is a cooperative mutation that can effectively test the binding code of scripting language. We find a bunch of bugs in this Adobe Acrobat, Foxit Reader, and Microsoft Word. And all tool is available online. If you're interested in finding bugs or get bounties, you can try. Let us know whether it helps or not. That's pretty much what I have today, and I'm ready for questions.